All right, my friends, let's do a quick review of the year in Algebra 2. The class was all about functions. We will look at shifting graphs of functions. So for example, if you have this f of x and you modify it by putting these other parameters a, h, and k around it, you'll notice that this negative sign in the front would flip the function upside down. The a value would stretch the function vertically by a factor of a. This h value would shift the entire graph to the right, and this k value would shift the entire graph upward. And so we'll look at a few specific examples of that later. We'll look at all these parent functions here that we met throughout the year. We'll look at radians and trigonometry, logarithms, zeros, wholes, and asymptotes. And that should set you up to do a pretty good job on your final. Well, first let's look at the idea of functions. So here's a function. F of x is x minus 3 squared minus 4. And what we could do with this function is, well, let's put an input of 2 into the function. Well, so there's the input of x equals 2. Well, functions change inputs that are usually the x value into outputs that we typically represent on the vertical axis, or the y value. Well, so if you plug a 2 in for x in this function, you'll get an output that is created at -3. So you can see if you put 2 in here, you'll get 2 minus 3, which would be -1. When you square that, you get 1. 1 minus 4 is -3. So there's the output of the function. The domain is the set of allowed inputs or allowed x values. And so if you look at this function, you could really put anything you wanted in for x. And, there's no problems or no restrictions. So it's all real numbers would be the domain. This parabola that's plotted here goes as far to the left as you want and as far to the right as you want. The range is the set of the allowed outputs. And notice that all of the outputs are, well, -4 or above. So you can't really be less than -4 as far as your outputs. And so the range goes from -4 inclusive, that's the square bracket for inclusive, all the way up to infinity. So anything above -4, or you could write it like this: y is greater than or equal to -4. We then looked at shifting graphs of functions. So say here is some graph of a function f of x that looks like this, and maybe you're supposed to graph -2 times the function. Well, what that will do is that will flip the function upside down and stretch it vertically by a factor of 2. So the original function I'm showing here with the dotted line and then the -2 times that function would actually look like this white curve. So let's look at a couple other examples. Say we had to graph -2 times f of x plus 3. The action of this x plus 3 is that is going to shift the function to the left by 3 units. Well, so if we start out with -2 f of x, which I'm showing here with dotted lines, well, then we have to shift this thing to the left by 3. And so -2 f of x plus 3 would look like this white curve here. Say we had to do f of x plus 5. Well, all that would do is, here's your original f of x, and it's just going to add 5 to every point along the function. So that's just going to shift it vertically upward by exactly 5 units. Finally, we could look at something where, like, say, 4 different transformations are happening. We have -2 f of x plus 3 and then plus 5. So what that's going to do, we'll notice -2 f of x is kind of right above this graph. So -2 f of x looks like this. But then what we have to do is we have to shift it to the left by 3 and up by 5. And so what that's going to do is move the graph over here. And so your final answer or final graph here would be this white curve. So that's what it means to kind of shift graphs around. We met a whole bunch of parent functions this year, things that you really should know roughly what the graph looks like. So the line y equals x, that's just going to be a diagonal line, a line with a slope of 1 and an intercept of 0. So if you needed to graph 1/2 x minus 1, well, that is going to vertically squish the function by a factor of 1/2, so it's going to flatten it out, and that's going to shift the function down by 1 unit. So notice the line has half the slope, and the y-intercept's been shifted down by 1. X squared functions, why those are parabolas, they look like this. You can play all these shifting games with parabolas too. So say we were supposed to graph -2 x minus 3 squared. The -2 is going to make it upside down and stretch it vertically. and the -3 is going to shift it 3 to the right. So it's going to look like that, shifted 3 to the right and upside down and stretched vertically. We also met powers of x. So x cubed, for example, looks like this. If you put in a big old positive number, you'll get an even bigger positive number. If you put in a big old negative number, you cube it, like you'll get a big negative number. So for example, -2, if you put in x equals -2, you'll get -8. Odd function graphs kind of look like this. Like x to the 5th looks pretty similar to this, x to the 7th as well. And then the even-powered functions all look like this. They approach, as you go to x equals positive infinity, the function will approach infinity. And as you go to x equals negative infinity, by the time you take that to an even power, that's going to make that into a positive number. We also met like square root functions, for example. A thing to notice about the square root function is it looks like the right-hand side of this parabola, but just reflected about the diagonal. And that's because the square root is an inverse function of the squaring function. So these two kind of undo each other, squaring and square rooting. When you have inverse functions, they'll be kind of reflected about this diagonal line. The thing that keeps it from being completely reflected about the diagonal line, which would give a branch down here, is that square roots can't be negative. So you only get this sort of upper branch. Whereas if you had a cube root, those guys can be negative. And so this cubed function, if you actually reflected it across the diagonal line, across the line that would go like this, you'd get a curve that looks like this. Exponential functions look like that. A good little point to know about these functions is if you take anything to the 0 power, so x equals 0, you'd have e to the 0 here, and that would be 1. So kind of a little anchor point for the parent function of, well, anything to the x power is the thing is going to cross through the point over 0 up 1. And you can transform these as well. So if you had negative e to the x minus 1, the negative would flip this thing upside down, and the -1 would shift it downwards. So you'd get something that looks like this. If you didn't have the -1 here, it would kind of be slightly above here. It would cross at 0, -1. But this is going to cross at 0, -2, because we're going to shift it down by another 1. Logarithms are the inverse function of exponentials. And so that's going to reflect an exponential function about the diagonal. And so those are going to look like this. So this would be, say, log base 10 of x. Or really, log base anything of x is going to look roughly like this. And you can transform these as well. So say you had log of x plus 1. The plus 1 here is going to shift it 1 unit to the left. And so that's going to look like this. It'll happen to go through the origin instead of through the point over 1 up 0. We looked at trig functions. The cosine function, for example, is a wave that starts at over 0 up 1, and it's a wave. You can transform these things, say, by graphing. If you wanted to graph -2 cosine of x, that's going to flip it upside down and make it twice as tall. And so that's what a transformed cosine wave might look like. The absolute value function, well, absolute values are always positive. And so if you did absolute value of x, it looks kind of like the line y equals x. Only this left-hand branch of y equals x, which would go negative, you have to kind of fold it up so it looks like this. So these absolute value functions kind of look like these. You can transform them as well. So if you had absolute value of x plus 3 and then add a 1 to it after that, the plus 3 will have the action of shifting it to the left 3, and the plus 1 would shift it up by 1. So these are the parent functions that we met this year. Let's look at radians and trigonometric functions. So big deal about radians to remember is if you go all the way around, that is 360 degrees, as you all know, but that's also 2 pi radians. Or another way to think of these radians, or just remember a conversion, is halfway around. So going that far around, that's half of 360 or 180, and that's the same as pi radians. So that's kind of my go-to concept or thing I think about if I'm trying to change things into radians. Well, so for example, let's look at if we were supposed to evaluate the cosine of pi over 2 radians. Well, pi over 2 is half of halfway, or a quarter of the way around, so it's right there. And the cosine function, if you remember, you peel off the x-coordinate on the unit circle. Well, so the x-coordinate of this point here on the unit circle would be 0. because it's at over 0, up 1. So the x-coordinate 0, so cosine of pi over 2 is 0. Say you had to do 11 pi over 6. Well, that is almost 12 pi over 6, which would be all the way around. So it's pi over 6 short of being all the way around. So it's right there. And so as it turns out, you have like a little 30-degree angle left over going all the way around. Well, if you're supposed to find the sine of that, you need to peel off the y-coordinate on the unit circle. And the y-coordinate here, you would be half of a unit down. This is a special angle of 30 degrees below the red arrow here. So you would be 1/2 of a unit below the x-axis. And so the y-coordinate here would be minus 1/2 of this point. And then finally, we have here the tangent of 3 pi over 4. So that's 3/4 of pi. That is 3/4 of halfway around. So that's going to be right there. And the tangent, the thing to remember with the tangent is you're basically peeling off the slope of this little arrow going to the unit circle here. So that thing's going to have a slope of -1. And so that is the tangent of 3 pi over 4. Then we looked at graphing trigonometric functions. As I mentioned, if you're looking at the cosine function, that peels off the x-coordinate of an arrow on the unit circle, all right? Well, so here we are at the tip of this arrow would be over 0, or excuse me, would be over 1 up 0, so the x-coordinate would be 1. Well, so when you're at 0 radians here, you would put the cosine, the value of the cosine as 1. For sine of x, you peel off the y-coordinate. Well, the y-coordinate here would be 0. And so sine starts at 0. And then for tangent, you peel off the slope. Well, the slope of this flat arrow is 0, so tangent also starts at 0. If we crank up a little bit to 45 degrees or pi over 4 radians, the x-coordinate would have shifted from being 1 to, well, it's not as far over. The x-coordinate's not as far over. So the cosine is going to come down a little bit. So it's not quite as high as this red point. Sine, which was 0, which is the y-coordinate, now we've grown in y. So now we're up here. That's our y-coordinate of the tip of that arrow. And then the tangent is the slope of that orange arrow, which you can tell that the slope here would be 1 if that's at 45 degrees. So that's going to start there. And then if we just keep going, so if you get to where this yellow arrow is at pi over 2 or 90 degrees, that is going to have an x-coordinate of 0. So cosine is 0 there. Y-coordinate will be maximized because you're over 0, up 1. So your sine wave is going to peak there. And then tangent is the slope, but the slope of a vertical line is undefined. It's going to blow up to infinity, basically, as you approach it from turning up this way. And then, of course, as we turn past that point, the slope would become like negative infinite. So tangent kind of blows up on this side, and it's going to come from negative infinity on the other side. And you can just keep cranking around. When you get to the green arrow, now we've got a negative x-coordinate, so cosine goes negative. We still have a positive y-coordinate, and now we've got a negative slope. So the tangent goes negative, and then keep going. The blue arrow, your x-coordinate's -1, so you've got a negative a valley here in the cosine wave, and the y-coordinate has gone to 0, so sine's going to go to 0 there. And the slope of that blue thing is 0, and so tangent is going to be at 0. And you can just kind of keep building things up like this. So as you keep cranking around, that would be the cosine, sine, and tangent of the blue arrow. Here's this like darker blue arrow. That's going to have an x-coordinate of 0, so the cosine function's back to 0. The sine is the y-coordinate, which would be -1. And the tangent would be the slope of this thing, which is now back to being a infinite slope since it's a vertical line. And so that's a way to build up these functions. There's the purple position, and then we'd be all the way around back to the red line, and that would kind of complete the, one full period of the cosine, a full period of the sine, and as it turns out, 2 periods of the tangent function. So there would be our cosine wave. There's our sine wave, and tangent will look like this. Again, tangent's the slope. So notice if you where we started here, we had a slope of 0. If you had tilted a little bit below the x-axis, it would have a negative slope. So for slightly negative angles, the tangent is slightly negative. And then it builds up. When you get to the red arrow, you have a slope of 0. The orange arrow has a slope of 1. The yellow arrow has an infinite slope. So tangent's going to just kind of blow up like this at pi over 2 radians, or 90 degrees. And then notice as you crank around, tangent will kind of blow up again when you get to the blue arrow, or pointing at 3 pi over 2 radians. What is that? 270 degrees. So that would be here. So you notice the period of the tangent function is just pi as opposed to pi over 2. So it repeats more often than the sine and the cosine. Logarithms were probably the newest and strangest thing in Algebra 2. So let's take a look at what the heck logarithms even are. So if you have something like log base 10 of 1,000, the thing you really want to think about is what this means is what exponent do you have to slap on this 10 to get 1,000? Well, so 10 cubed happens to be 1,000. So the exponent you'd put on 10 to get to 1,000 would be 3. So we know 10 cubed is 1,000. And so the log base 10 of 1,000 is 3. Again, it's the exponent we must put on the base in order to get this number of 1,000, the argument of the function. So let's look at a couple examples. Say you have log base 10 of 5,000. So it's like, well, what exponent do we have to put on the 10 to get 5,000? Well, we know that 10 cubed is 1,000 and 10 to the 4th is 10,000. So what that means is log base 10 of 5,000 has to be somewhere between 3 and 4, because 5,000 is, well, between 1,000 and 10,000. And it turns out if you punch that into a calculator, you do get between 3 and 4. You get 3.69897 if you round to that digit, I guess. So that came from the calculator. Let's look at a couple specifics. So log base 10 of 10 means what exponent must we place on 10 to get 10? Well, 10 to the 1st is 10. So the exponent you put on 10 to get 10 is 1. The next one, log base 2 of 16. Oh, sorry, I guess we'll do this one next. log base 3 of 1/9. What exponent must we place on 3 to get 1/9? Well, that is the reciprocal of 3 squared. So the exponent is going to be -2. So 3 to the -2 is 1/9. Next one, which exponent must we place on 2 to get 16? 2 times 2 times 2 times 2. So that's 2 to the 4th is 16. So the exponent you'd put on the 2 to get 16 is 4. Next, we get ln of e to the 6. Whenever you see ln, natural log, that is log base e. So it's saying, what exponent must we place on e to get e to the 6th? Well, I would just place a 6 on e to get e to the 6th. So the natural log of e to the 6 is just 6. Now, here we have log base a of cube root of a. What exponent must we place on a to get a to the 1/3, which is what cube roots are? Well, I would place a 1/3 on a to get the cube root of a. And so the log base a of cube root of a is 1/3. And then finally here we have log base a of 1. What exponent should we put on a to get 1? Well, anything to the 0 power is going to be 1. So we must get an answer of 0 here. So what are logarithms in general? Again, it's what exponent you would put on the base to get this number. So we had from before that 10 to the 3.69897 is pretty close to 5,000. A neat little thing to notice is, so log base 10 of 5,000, that's the same as log base 10 of 5 times 1,000, which, as it turns out, is log base 10 of 5 plus log base 10 of 1,000. So log base 10 of 5 is, well, what exponent must you put on 10 to get a 5? It turns out that is a number less than 1. So 10 to a power less than 1 will get you to 5, and it's this funny decimal. And then the second term here says log base 10 of 1,000. Well, it's what exponent must I put on 10 to get 1,000? That's going to be 3. So 10 cubed is 1,000. So you get this quirky little rule that log base 10 of 5,000 is the same as log base 10 of 5 plus log base 10 of 1,000. And so what that means is we've just learned something useful in general. If you're taking a log of a product, log of a times b, that'd be the same as log of a plus log of b. And you can see how that worked up above, where the log of 5,000 was the same as the log of 5 plus the log of 1,000. So that's a useful little rule with logarithms. So in general, what are logarithms? If you ever see log base a of b, that means what exponent must I place on a to get b? Let's finish up here by looking at zeros, undefined points, and wholes in functions. So suppose we have this function f of x equals the product of x minus 1 times x minus 3 times x minus 5. This function is written in a factored format. What's useful about this is at any point where any individual factor is 0, the entire function has to be 0. So if you graph this function, it's going to have zeros at x equals 1, because that would make the first factor 0, x equals 3, which would make the second 0, and x equals 5, which would make the third factor 0. So here is a graph of the function, and notice that we have zeros at x equals 1, x equals 3, and x equals 5. So that's the value in learning to factor a function. On the right here, we have this more complicated function, g of x. Well, something to notice here is that the function is going to be undefined at x equals 2 and x equals 5. And the reason is, well, you can't divide by 0. Then the function will become undefined. So if you have factors in the denominator, the function will be undefined at places where the factors in the denominator are 0. So the function will not be defined at x equals 2 and x equals 5. Now, something interesting here is you notice that one of the factors here, x minus 5, that makes the function undefined at 5, happens to be repeated here in the numerator. It shows up in the numerator. When that happens, you'll have what's called a hole in the function. So if we look at a graph of this thing, what you notice is, well, indeed, the function's undefined at x equals 2. It blows up there. It approaches infinity from x coming from below and negative infinity with x coming from above. So the function is undefined at x equals 2, but then also you have this hole up here at x equals 5, right? And notice that we have zeros at x equals 1 and x equals 3 because that will make the factors in the numerator go to 0. So there's the 0 at x equals 1, and there's the 0 at x equals 3, and that's from these two factors that appear in the numerator. Right, let's look at another quick example of this. So you have g of x is x plus 3 over, well, x squared minus 3x minus 18. The thing you're going to want to do first before trying to, say, graph this thing is let's factor the denominator. And so when you do that, well, to factor this, right, you need two numbers that multiply together to give negative 18, but add together to give negative 3. And so that's going to be minus 6 and plus 3. So you ought to know how to factor at the end of Algebra 2. And what you notice is we have this repeated factor of x plus 3. It appears in the numerator and it appears in the denominator. So there's going to be a hole at x equals negative 3 at the point where the function here is like, well, undefined at x equals negative 3. It is also going to be undefined at x equals 6, but it won't be a hole. It's going to be a place where the function like blows up to plus and minus infinity, and then like I mentioned, you'll have this hole at negative 3. So if you graph it, you see that indeed the function sort of blows up at x equals 6. Coming from above, it would go to positive infinity. Coming from below to negative infinity. So the function is not defined at x equals 6, which would make this which would make us divide by 0, but is also not defined at x equals negative 3. There's a hole here, again, because of this factor that appears in both the numerator and the denominator. So there's that hole. So the function looks a lot like the function 1 over x minus 6. In fact, it's exactly the same as that function, except for the existence of this hole. So the function written above here is not exactly the same as 1 over x minus 6. It's just the one distinction between the original function and 1 over x minus 6 is that there is this additional point here where the function is not defined. So thank you all for watching, and good luck on your Algebra 2 final.